Everything we've talked about up to this point, in terms of Newton's laws and kinematics, has been in terms of linear motion. Even when we talked about two-dimensional projectile motion, we broke everything into x and y components so that we could just deal with linear motion in the x direction and linear motion in the y direction. So the result of that we had was something like we see in this first figure here. What we previously looked at for equilibrium, we said, well, the sum of the forces in the x direction or in any direction were equal to 0. This meant that our acceleration was equal to 0 and we had equilibrium, which is what we have in this case here. If we have a coordinate system, a traditional coordinate system like this, then we have the sum of the forces. We have a positive F to the right and negative F to the left, and these forces cancel out and we have equilibrium conditions here. However, we need to, in order to fully describe motion, we need to not only talk about its linear motion or what we call translational motion. So translational motion is what we've looked at in the past, translational. We need to now look at also rotational motion. So we need to look at this now. So everything, chapters 1 through 8, we're focused on translational. Rotational motion will be chapters 9 and 10. So if we were to take kind of the same figure here with the hockey stick and the two forces acting on it, and we just change how we apply these forces a little bit, then we would see here, so we have again a force off to the right and then a force off to the left, but now these are offset from each other a little bit. And I think that just from everyday experiences, we would know that if we apply forces like this, we would have some rotation of this hockey stick or another object. We would have a rotation which would be in the counterclockwise direction, kind of going around. Actually, sorry, the clockwise direction. Yes, I'm going around like that in the clockwise. So we would no longer consider this hockey stick to be in equilibrium. It is in translational equilibrium because the sum of the forces are equal to 0, but there seems to be something causing it to rotate. So it's rotational. It's not in rotational equilibrium. So rotation accelerates here. So we need to look at what causes this rotation. And it seems to have something to do with the displacement between these forces. When these forces were in line, we had no rotation. But now that these forces are offset from each other, we have some rotation. So we need to take a look at what is the cause of this rotation. And the thing that causes rotation is something we call torque. So let's define this here. So torque, which we symbolize by a Greek letter tau, is a force times a distance away, or a moment arm. So, and this force here is perpendicular to this moment arm. And so this is the force, and this is the perpendicular component of the force times what we call this is the lever arm or the moment arm. Sometimes a torque is called a moment, so that's why this is called a moment arm sometimes, but either one of these work. It's essentially a distance away, how far away the force is applied. So you can think about like opening a door. Oh, and by the way, the units of this, the units of force would be in newtons. The units of this lever arm are in meters, so this is Newton meters. Now, we've previously said that this is a joule, but for torque, we leave it as Newton meters just to be very clear that we're talking about a torque as opposed to an energy. Although a torque will create it leads to a change in energy. We'll talk about this later on. We leave the units as Newton meters. That way we're very clear we're talking about a torque. So let's think about opening a door like we have in this next figure here. So we have the hinge. So this door will open, rotating around the hinge, something like this, in a counterclockwise fashion. And we have this force F, right? Right here. And remember, the length of this arrow represents the magnitude of the force F, so the size of that force F. And then we have R over here is our moment arm, or our lever arm. Okay, so the torque created about this hinge, we have to talk about, when we talk about torques, we have to talk about torque around a certain point. We'll talk about this a lot more in the next video. But the torque created by force F around the hinge would be this force, the force F. So the torque, I'll say around the hinge. So the torque created around the hinge, or about the hinge, will be the force times the lever arm. So force times R. And it has to be the component of this force which is perpendicular to the door. So perpendicular force times the door. Now this is drawn perpendicular here, so it's the entire force times the moment arm. If I were to apply a different force like this, we can see that, well, that would be, not as an effective way, be a less effective way to open the door, right? Because now we have our force here, and it is not all perpendicular. It would only be the perpendicular component of that. So we'd have to say, well, it'd just be this portion of the force perpendicular times this lever arm here. And the parallel component of this force, we'd have also some force which is parallel, and this would cause absolutely no torque around the hinge because it is not perpendicular at all, right? It has to just be the perpendicular component of that force. So yeah, the torque created about the hinge by the force is the perpendicular component of the force times the moment arm. If we were to have this force closer, clearly this would create less of a torque. We know that we'd have to, it would be more difficult to open the door if we were pushing over here closer to the hinge, and this is because we have a smaller lever arm. Same thing about pushing it off at an angle. I'd have to push harder here. Okay, so some other ways we can define the torque. So we see here, we have a force. Let's say this is rotating around this point right here. So the moment arm is it's a vector, and it's drawn from the point of rotation to any point on the line of action of the force. Let me define the line of action. The line of action of the force is simply a line which goes through the force. So this is the line of action of F. Same is true up here for this force. This would be the line of action, the blue in there. So these are lines of action of the force. So we have, this is the line of action of the force F. Okay, so we have the torque created here in figure A. The torque created, since the moment arm is perpendicular, it's just the entire moment arm times the force, and these are perpendicular to each other. Another way we could have defined this, if we have this angle, the angle between the force and the moment arm, if we call this angle theta, then the perpendicular component of this force, the perpendicular component of that force would be the F sine of theta. So we could have said here that the torque is equal to the perpendicular, the component of the force perpendicular to the moment arm. Or we could have said this is since the component of the force which is perpendicular is F times the sine of theta, where theta is the angle between the force and the moment arm, is F sine of theta times R. We can also call this FR sine of theta. Or if we wanted to, we can also call it the force times the component of the moment arm, which is perpendicular to the force. Right? So as long as the moment arm and the force are perpendicular, this is the important thing. So if we look here and we see, just for example here, we have in figure E down below, we have the force acting off to the left here. Its line of action would look like this. And we have this angle theta between the lever arm or the moment arm and the force. And if I wanted to find out what the torque is, I would just take my component of the lever arm, which is perpendicular, so that would be this right here. This is perpendicular to the force, and the length of this moment arm would be r times the sine of theta. So this is r sine of theta right here. So then the component of the moment arm perpendicular to the force is r sine of theta, and so we have our torque here equal to the force times the component of the moment arm perpendicular to the force, so this is r sine of theta. So many ways that we can write out the torque here. We have torque is equal to perpendicular force times the moment arm, or this is the force times the perpendicular component of the moment arm, or we can say this is F times R times the sine of theta, where theta is the angle between the moment arm or the lever arm and the line of action of the force. So all of these are true. I think the easiest way to go about it is probably this first definition. Just break the force into components which are parallel and perpendicular to the moment arm, and take the perpendicular component times the force. And then when we do this, we see, like we have in figure F here, we see if I have a force which is parallel, so here's the point of rotation, and we have our lever arm is like this, and the force is parallel to this lever arm. So since this force is parallel, they'll create no torque whatsoever. If I were to plug this into the equation, torque is equal to Rf sine of the angle between the lever arm and the force would be 180 degrees. And so then the sine of 180 is equal to 0, so this is 0. There is no torque created about that point. So lastly, we need to talk about the sign convention of torque. So this is our sign convention here. We have a positive x. This is typical sign convention. Positive x is this way, positive y is up this way, and we actually have a positive z. Sticking with standard convention, a positive z comes out of the screen here, out of the page. And torque is actually a three-dimensional thing. So the direction of torque is actually, if we have something rotating around like this, it's actually out of the page, which we call the positive direction. So we define this to be the positive direction. So if we have a torque which goes around counterclockwise, so a counterclockwise, CCW for counterclockwise, is the positive direction. This is positive torque. So clearly if we have a clockwise direction, so if we have something that creates a clockwise torque, this is clockwise is a negative torque. So clockwise is negative and counterclockwise is positive. And the way to see if it is positive or negative, let's say that we just have something like this. Let's say that I have a bar here that is penned at this edge. This is very similar to the hinge in the door. And I apply a force like this. Now, if I were to hold this point is not going to move, but everything else is going to move. And I push off, I try to move off in this direction, but I have to remain the same distance away. Then we would see that in order to stay the same distance, I must be rotating around like this. So this would be a counterclockwise torque, or a counterclockwise rotation. So this would be a positive torque. If we were to flip that around, though, we have a force which is applying down here, then this one, if I try to move in the direction of the force, but I try to stay equidistant from the point of rotation, I would need to come down and like this. And so this would be a clockwise direction, so this would be a negative torque. So in torque and in all rotational motion, we define counterclockwise to be positive and clockwise to be negative.